All right, so last time we talked about moles, counting atoms, ions, and molecules in groups called moles, and how we do it in the lab from if we have samples of a pure compound. So we figured out how much solid we were going to need if the compound was in the form of a solid, or how much liquid we would need, what volume of liquid we would need if the compound happens to be available as a pure liquid. So today we're going to look at how we can determine moles from solutions. Okay, so we're going to introduce a concept called molarity. First of all, let's define what a solution is. A solution is a homogeneous mixture. Okay, so it's two or more substances mixed together into a homogeneous sample, so you can't tell one component of the mixture from the other. The predominant component of your solution is called a solvent, and everything else are called solutes. Okay. If your solvent happens to be water, then what you have is called an aqueous solution. So imagine you have a solution you prepared by stirring a pinch of sugar into a glass of water. What would be your solute and what would be your solvent? So your solvent would be water, okay, and your solute would be the sugar, okay. Let me see if I can show you an animation of that. Go to phet.colorado.edu. And you go to, oh, we've seen this before. Here's salt and sugar solutions. Let me bring up one that involves molarity. Okay, while that's loading, let's just continue. If you go to the lab, chances are you're going to see your samples in a bottle that has a label on it, and that label happens to be what's called the molarity. Okay, I think I got my animation going here. So here's an example of how, just to give you a visualization of what happens when you have, when you're making a solution in the lab. So if you shake some solid into water, okay, you can see it's evenly dispersed throughout the water. What you get is a homogeneous solution. Okay, so you can measure the concentration, which will tell you how many moles you have of a particular solute in your solution. Okay, and in this animation, you can just do it by dragging this thing right here. And this says it's got 0.900 moles of your solute in a liter of your solution. Okay. So anyway, if you go to the lab, you might see a label on the bottle that looks like this, 0.1 big M NaCl. You would read that as 0.1 molar sodium chloride. What that label means is that if you have a liter of this solution, then it's going to contain 0.1 moles per liter. So a big M right here is called the molarity. It tells you how many moles you have. So N is the number of moles. V is the volume in liters. Okay, so molarity is moles per liter. Okay, it can also be, so a big M is abbreviation for the unit moles per liter, which you can write as moles times reciprocal liters, or it can also be millimoles per milliliter. You'll notice milli will cancel out. That will still give you moles per liter. Okay, so the solution we have here, if you had a liter of this, then 1 liter will contain whatever the molarity is. So it will give you 0.1 moles of the solute. In this case is sodium chloride. So since molarity is moles per liter, okay, then the number of moles of solute, we can rearrange this equation. We solve for N. Molarity is moles over volume, right? Moles per liter. You multiply both sides by volume, then that counts as volume. You can solve for the number of moles. It's just molarity times volume, or volume times molarity. So if you have a solution in the lab and it has a label on it, the molarity is given on it, then you can figure out how much solute a given volume of that solution will contain. Okay, so let's illustrate that with this one, this example. How much sodium carbonate is in a 2-liter sample of 0.2 molar sodium carbonate? Then you just say the number of moles is equal to molarity times volume. So molarity in this case is 0.200 moles per liter. So that's what molarity is. Times the volume that we have is 2.00 liters. So if you cancel that, if you multiply that, you cancel liters, and you get an answer of 0.400 moles. As you can see, let's see if this makes sense. If you have 1 liter, okay, if you had 1 liter, it's going to have 0.200 moles. So it only makes sense that if you have 2 liters, you're going to have twice as much, 2 times 0.200 moles. So that's another way of looking at it. Okay, so number of moles is however many liters you have multiplied by the moles that you would have per liter. So number of moles of solute in a given solution is just molarity times volume. If you're using milliliters as your volume, then you get the answer in millimoles. Now, how many grams would this be? Figure out how many moles of sodium carbonate we have in the solution. Then to figure out grams, all you have to do, I think I can turn on your mic just in case you want to ask questions. Okay, so if you have, did I start recording? Yeah, I did. Okay. All right. So, how many grams would that be? How would you change that to grams if the question was asking for grams? Then let's review. What would you have to do? You need the molar mass, right? So times gram, however many grams per mole, that would give you the actual grams. So what's the molar mass of sodium carbonate? You go to your periodic table, you look up sodium. Molar mass of sodium is 22.99. You've got 2 of those. So that's 40, what is it? 45.98 grams in 1 mole of sodium carbonate. We'll have 2 moles of sodium. It's going to have 1 mole of carbon. And if you check your periodic table, a mole of carbon is 12.01 grams. So times 1, you got 1 carbon, 1 mole of carbon. So that's 12.01 grams. And if you have 3 moles of oxygen, so 16.00 grams per mole times 3 moles, that's 48.00 grams of oxygen. So that gives us a total of, let's see, 45.98, oops, plus 12.01 plus 48, 105.99 grams per mole. Okay? So if you convert moles of sodium carbonate to grams, so you would have, all right, so you say you have 0.400 moles of sodium carbonate. Change that to grams, then you say 1 mole of sodium carbonate weighs 105.99 grams. All right? So if you did that calculation, you get 105.99 times 0.4. That gives you 42.396 grams. Now you have 3 sig figs here, so you only need 3 sig figs. So the answer is 42.4 grams of sodium carbonate. Okay, so that's how you'd figure out how many grams you will need. Okay, so that means if I were to tell you to go to the lab and make me some 0.2 molar sodium carbonate, the first thing you'll have to ask me is how much, how many liters. So let's say I tell you make 2 liters of 0.2 molar sodium carbonate. Then you say, okay, I need 2 liters, so I figure out how many moles I need, and then I figure out how many grams I would need based on the moles. And then what do? You go to the lab, you weigh out 42.4 grams, you put it in a flask, okay, transfer it to a flask. So you put your 42.4 grams in your flask right here, and then you add enough water, bring it up to 2 liters. So you find a flask that can hold 2 liters of solution, okay? So that's what you have to do to make that kind of solution in the lab. Figure out how many moles you need based on the number of moles that you need. Figure out how many grams you have to weigh out for the solid, and then weigh out the solid, and then add enough solvent, add enough water to bring it up to your desired volume. Okay, so here's a question. How many moles of sucrose does a 25 milliliter sample of 0.5 molar sucrose contain? So same thing. Number of moles is molarity times volume. What's our molarity here? 0.5. 0.00 moles of sucrose per liter times 25 mils. Now 25 mils, a quick way to change that to liters is to say 25.0 times 10 to the negative 3 liters. Okay? A milliliter is 10 to the negative 3 liters. That's a convenient thing to know for calculations if you're dealing with mils. So what's 0.5 times 25? Okay, liters will cancel out, right? So that's 12.5 times 10 to the negative 3 moles. Or you can say that's 12.5 millimoles, okay, because 10 to the negative third mole is a millimole. Now, if you just, since you're being asked for actual moles, what would you have to do? This would be your actual answer in terms of moles. Then you say that, you just change this. You just say that's that's going to be what? I'm going to move my decimal point one place to the left to make that a number between 1 and 10. So that's going to be 1.25 times 10 to the negative 2 moles. Okay? So that's how much sucrose you have in a 25 ml sample of 0.5 molar sucrose. Now, what if you're dealing with ions? Sometimes you're interested in the concentration of ions, so moles of ions per liter. Then all you really have to do is multiply the moles of your solute, which would be an ionic compound, by the subscript of the ion in the formula. Okay, so first calculate the moles of the solute that you have, and then multiply it by the moles of by the subscript. So for example, let's look at this one. How many moles of barium chloride are in 2.00 liters of 0.3 molar barium chloride? Then you're going to say, all right, so number of moles of barium chloride equals 2.00 liters, volume times molarity, 0.300 moles per liter. So liter cancels out. That gives you 0.600 moles of barium chloride. Okay, now we're interested in chloride ions. So what would you have to do? Okay, you do one more step. You change moles of barium chloride to moles of chloride ions. So 0.600 moles of barium chloride multiplied by 2 moles of chloride in 1 mole of barium chloride. So you would expect twice as much chloride, and the answer here is going to be 1.20 moles of chloride. Okay, so this is really just reviewing what we did earlier. If you can count how many the moles of formula units that you have, you can multiply it by the subscript of the ion. That gives you the actual count for the ions. Okay. All right. If you need to calculate molarity of anything, all you really need to do in general then is to just divide however many moles you have by the volume in liters. Okay. So let's look at another example. Here's another example. Let's say you have a 2-liter solution containing 0.4 moles of sodium hydroxide. What's the molar concentration of sodium hydroxide? Then it's fairly straightforward. You just have to remember molarity is moles per liter, right? So moles is 0.400 moles of solute, which in this case is sodium hydroxide, divided by 2.00 liters of solution. So 0.4 divided by 2, that should be 0.2. And I have 3 sig figs up here, 3 sig figs down here. So that should be 0.200 moles per liter, or 0.200 molar. Okay? What if you want to know the molar concentration of ions? Then whatever the molarity of the compound is, you just multiply it by the subscript of the ion. That will give you the molarity of the ion for that compound. Okay, so example. You have 0.500 moles per liter of sodium sulfate. What's the molar concentration of sulfate ions? So you would say, okay, concentration of sulfate ions. Okay, when you use these square brackets right here, okay, around the symbol for an ion, that means the molar concentration of whatever is inside the bracket. Okay, so in this case, you're dealing with the molar concentration of sulfate. We can just say, okay, that's 0.500 moles of sodium sulfate. Oops, let me get this up a little bit. Moles of sodium sulfate per liter of solution, right? Well, I just need to convert that to moles of sodium. So I say there's 2 moles of sodium in 1 mole of sodium sulfate. Okay? Sodium sulfate, you can see there's 2 moles of sodium in a mole of sodium sulfate. So cancel moles of sodium sulfate, and that gives you a concentration of sulfate ion equal to 1.00 moles per liter of sodium ions. Okay. Now, if you have the square brackets around the symbol for the ion, you can just say that's 1.00. And that's implied that if you're using square brackets, that your unit is moles per liter. So this would be acceptable. Although there are some who are picky about this and they really want you to specify moles per liter. Okay, but it's as far as I'm concerned, that's really obvious. By putting brackets around it, you're specifically referring to the molar concentration, so the unit should be implied. All right, what's the molar concentration of chloride ions if you have a mixture that doesn't contain just sodium chloride but also contains barium chloride? So you have a solution, it has barium chloride in it and sodium chloride. Now, if you remember, if you put these compounds in water, your barium ions are not going to be clustered with your chloride ions. They're all going to be separate from each other, right? And so will your sodium and your chloride ions. So if you want the molar concentration of chloride, you can see that you have 2 sources here. So you just add up the concentration of chloride coming from the sodium chloride and the concentration of chloride that's coming from the barium chloride. You just add them up. Okay? So you would say, in this case, okay, you would say concentration of chloride equals chloride from sodium chloride plus the concentration of chloride coming from the barium chloride. And what do? You just say concentration of chloride from NaCl is 0.10 moles per liter NaCl times 1 mole chloride for 1 mole of NaCl. Okay, so that gives you moles of chloride per liter coming from the sodium chloride. And to that, you add from your barium chloride, you have 0.2 moles per liter of barium chloride. So you say plus 0.20 moles of barium chloride per liter times 2 moles of chloride for 1 mole of barium chloride. Why 2? Because barium chloride has 2 chlorides. Okay, sodium chloride has just 1 chloride. And so that gives you 0.1 0.10 plus 2 times 0.2, that's 0.40 moles of chloride per liter. You'll notice your sodium chloride cancels out, and so does your barium chloride. Okay, so the total chloride concentration, you say, in this mixture is 0.50 moles per liter. So molar concentration of chloride is 0.50 molarity. Okay. Frequently in the lab, you'll find solutions instead of a pure substance. So if you want to make a solution, another solution, one way you can do it is to do what's called dilution. Dilution simply means adding more solvent to a solution. What it does is it lowers the concentration. So if you have generally you would have a stock solution in the lab, okay? And you can use that to make solutions that have a lower concentration. And the process of doing that is simply adding more water. Because if you add more water to your solution, you just increase the volume without changing the amount of solute. So when you're doing dilution, you have the same N, same moles of solute. All you're doing is adding water. You're just adding more solvent. But by adding more water, you're increasing the volume. So your molarity, which is moles over volume, will decrease because this will stay the same, but your denominator here will become larger. So your molarity ends up being smaller. Okay? So dilution is commonly used in the lab to prepare a solution if a more concentrated solution is available in stock. Okay? So the idea here is you have a stock solution in the lab, and then you add more solvent to it, you get a more dilute solution. So dilution, like we said, in dilution, the number of moles doesn't change. So moles before, which would be volume times molarity, before you add your solvent, before you do your dilution, must be equal to the moles of solute after you've added the solvent. The amount of solute is unchanged. So this one says moles before equals moles after. Moles before dilution equals moles after dilution. Okay. So what's the molarity of the resulting solution if 1 liter of 2 molar sodium hydroxide is diluted to 4 liters? Let's look at this example. So the idea here is you have a liter of solution. Okay. So you put 1 liter there. 1 liter of 2.00 molar sodium hydroxide. And then you add enough water, more water, so that you bring up your total volume to 4 liters. Okay? This is not drawn to scale, but you get the picture. Let me draw it to scale. So you have 1 liter of your solution, and then you add more water, so that's 2, 3, 4. You add more water, so that becomes 4 liters now. What would be the molarity of the resulting solution? You'd expect it to be lower. And how low would it be? You say you're doing a 1:4 dilution here, so you would expect your concentration to be only a quarter of what it was. And you can see that by using the dilution formula. You can say M1V1 equals M2V2. So what do I have before? 1 liter, 2 molar. Okay, so before I did my dilution, I have 1 liter, and I have 2 molar, 2.00 molar. That's the molarity before. Okay, and after, I have I don't know what the molarity is after. That's what I'm looking for. I'm interested in that, the resulting solution. But my final volume is now 4 liters. So V2 is going to be 4.00 liters. So now I can solve for molarity of my diluted solution. What's the molarity of my diluted solution? How do I solve for M2? You just divide both sides by V2, which is 4.00 liters. Okay, so 4.00 liter cancels out. So M2 is equal to 2.00 moles per liter times 1.00 liter divided by 4.00 liter. And liter cancels out. So you can see you end up multiplying your original molarity by 1/4. So you get a quarter of 2, which is what's a quarter of 2? That's 0.500 moles per liter. Okay, so from a 2 molar stock solution, you're able to make a solution that's less concentrated or more dilute by simply adding more water to it. That's called dilution. Okay. Now, there are other concentration units that you might encounter in the lab. So, for example, you might encounter a bottle that tells you what the percentage is by mass, and sometimes it's labeled as percent W/W. That's weight by weight. Okay, so what that really means is percentage by mass. So whatever that number is, that will tell you how much solute you have in 100 grams of mixture. Let's take a look at this example right here. Let's say you have a reagent bottle that says it contains hydrochloric acid, HCl, and then it's 37% hydrochloric acid by mass. And the specific gravity is 1.19. We'll ignore this for now. Okay. Let's figure out how much HCl we need to dispense if we want 0.2 moles of HCl. Well, let's see. How do you get moles of HCl? 0.200 moles of HCl. Okay. You can convert that to grams first. Okay. So how many grams of HCl would you need then? You would say, how do you go from moles to grams? You need molar mass, right? So HCl, 1 mole of H is 1.008 grams. 1 mole of chlorine is 35.45 grams. You look this up from your periodic table. So that gives you a total of 36.458, or that would be 36.46 grams per mole. Okay, 36.46 grams per mole is the molar mass of HCl. So how do I change 0.2 moles to grams? So I say 0.200 moles of HCl, change that to grams. So it's 36.46 grams per 1 mole of HCl. So 36.46 times 0.2, 36.46 times 0.2 is 7.292 grams. Okay. Keeping in mind I only have 3 sig figs here, so my 9 is really my last sig fig here. I'll have only 3 sig figs. I'm going to keep that 2 because I'm going to carry this into another calculation. So I figured out how much HCl I need. Okay? Based on if you know the moles that you need, you can always figure out how much of the substance, how many grams you need. Because I need 0.2 moles of HCl, then I need to weigh out 7.29 grams of pure HCl. The problem is I don't have pure HCl. My bottle says it's only 37% HCl. If I had 100 grams of that HCl, of that solution in the bottle, only 37 grams of that would be HCl. So what I have to do is figure out how much of solution I need. So I'm going to say, okay, 7.292 grams HCl. I have to take it from a mixture that's only 37% HCl. So I can use this conversion factor right here, 37%. Okay, that means, okay, that means that 37% by mass simply means that I'm going to get 37 grams of HCl in 100 grams of solution. So that's the equivalence. Okay? So if 100 grams gives me 37, okay, I can just multiply this by 100 grams of solution over 37 grams of HCl. This will allow me to figure out how much solution I need to weigh. So that will give me how much? 729.2 grams of solution. All right. Keeping in mind again that the 9 here is my last sig fig. I only have 3 sig figs. I'm keeping an extra digit here because I need to carry this over to another calculation. So I'm going to need 729 grams of solution. Okay. All right. So what do I do next? I can go to the balance, weigh out 729 grams of solution. I can get a beaker, a big beaker, put 729 grams of HCl in that beaker. All right? But it's generally not advisable to do that when you're dealing with liquids because if you okay. Oh, I did not divide by, oh, I'm sorry, I did not divide by 37. I'm sorry. I was wondering why that number was so big. Okay, what's 729 divided by 37? 729.2 divided by 37. I was wondering why that was so big. Thank you. 19.71. Okay, so it's 19.71. Is that better? Thank you. So 19.71 grams, keeping in mind, like I said, that we only have 3 sig figs, so it's really 19.7. Okay? So what do I do now? What I do is I go to the lab, like I said, and take a beaker and put 19.71 grams of concentrated HCl there, or 19.7 grams. And as I mentioned just a while ago, it's not really advisable to do that with liquids because you spill the liquid, you ruin an expensive piece of equipment. Your balance gets ruined. Okay? And so what you prefer to do is just determine how much volume you would need since this is a liquid. Especially HCl, concentrated HCl is a corrosive acid. You really don't want to weigh it. Okay? So what you can do is you can change that to volume. So how do I change grams to volume? I need to know the density. Okay? So specific gravity, okay, if you see specific gravity on the bottle, that is essentially the density in grams per mil. Specific gravity is defined as, okay, specific gravity is equal to the density of something in comparison to the density of water, of some reference liquid, usually water. But since the density of water is 1 gram per mil, whatever the specific gravity is, that's actually the density in grams per mil. So what that means is you have 1.19 grams of solution in 1 milliliter of solution. So that information right there is what you can get from the label on the bottle. If it says 1.19 is the specific gravity, that means if I took a 1 milliliter solution, a sample of that solution, it's going to weigh 1.19 grams. Okay? So I can just change my grams to mils. So I would say 19.7 grams. Change that to milliliters. I'm going to say 1 milliliter is going to weigh 1.19 grams. So grams is going to cancel out. So 19.7 divided by 1.19 is 16.5, 16.6. So this is what I'll do in the lab. I'm going to take 16.6 milliliters of solution. Okay. I'm going to put that in a graduated cylinder. I have 16.6 milliliters. All right. And then I add enough water to that to bring it to whatever total I will need. Okay, we're not making a solution here. We just say how many mils you need. So that's how much you need. Whatever, if you need 0.2 moles, that's how much you're going to need. Okay. So you take 16.6 mils, and that's it. You got your 0.2 moles. Now, as a follow-up question to this, what's the molarity of your HCl solution? This concentrated stock solution that you have. Well, molarity is what? Moles per liter, right? Moles over volume. And any sample of your solution, the ratio of moles to volume would be the same. So if I were to have, let's say, 100 grams, okay, so, well, actually, let's assume you have a liter of solution, okay? So remember, that's moles per liter. So you assume you have a liter of solution. What would be the mass of that? Sure, okay. The mass is 1,000 is 1 kilogram, right? 1,000 grams, because 1 liter is 1,000 milliliters. I'm sorry, it's not 1,000 grams. Sorry. The mass is going to be what? Mass of solution equals 1,000 mils times our density is 1.19 grams per mil. Okay. So you just use your density to figure out the mass of your solution. That's your specific gravity. And so that gives you the mass of the solution that you need is 1,190 grams of solution. Of that, how much is HCl? You say that the mass of HCl, the actual HCl, is only 37% of that, right? So what's 37% of that number? You say it's 0.37 times 1190 grams. So that gives you 0.37 times 1190. 0.37 times 1190 is 440.3 grams. 440 grams, 3 sig figs. We're assuming our percentage is exact, and we have 3 sig figs in 1190. Okay? And then you can change that to moles of HCl. Would be 440.3 grams. Okay, what's the molar mass of HCl? 1 mole of HCl we figured out earlier was 36.46 grams. The molar mass of HCl is 36.46. And this gives us a moles of 440 divided by 36.46, that gives you 12.1 moles per liter. Okay? And that's pretty much how HCl is sold commercially. Concentrated HCl is 12 molar HCl. So you can use that instead as a basis for figuring out how many moles, how many mils you're going to need. Okay, so if I have 12.1 moles per liter, there's another way I could solve the original problem. I'm just going to say if I need 0.2 moles, okay, molarity, okay, moles is equal to molarity times volume, right? If I want 0.2, if I want this to be 0.2, then I just say the volume I need is N over M, okay, 0.2 moles divided by 12.1 moles per liter. And that should give me 0.2 divided by 12.1, oops, 0.0165 liters, which is the same thing as 16.5 milliliters. Okay, there's just a little bit of a discrepancy here in the last sig fig, but that's okay. Remember, we're uncertain about that last sig fig, so that's just a round of error that built up because I did not keep the extra digit there. Okay, so this is another way I could have solved the problem. I could have known right away. Actually, I already know that it's 12 moles. It's 12 moles per liter HCl. But oftentimes, what you see on the bottle is not 12 molar, but you'll see that it's 37% HCl by mass. Okay, so there's a question about an HCl bottle that says 0.1 molar and another one that says 0.1 normal. Okay, 0.1 molar means it's got 0.1 moles per liter. Okay, if the bottle says, okay, some bottle you'll find has what's called the normality. This is called the normality, and that's 0.1 equivalents per liter. Now, 1 equivalent of an acid, okay, will give you 1 mole of H plus ions. Okay, so that means 1 mole, 1 equivalent of HCl, okay, is the same thing as 1 mole of HCl. So as far as HCl is concerned, 0.1 molar, okay, so this is 0.1 molar, that's the same thing as 0.1 normal. Okay, so this is the normality. So you say this is 0.1 normal. But if you have sulfuric acid, okay, let's say you have 0.1 molar H2SO4, okay, this is going to give you 0.2 moles of H plus, because there's 2 moles of H in H plus ions that you can get from H2SO4. So 0.1 molar sulfuric acid is 0.2 normal sulfuric acid. Okay, so in a lot of normality is an old way of referring to concentrations, and it's rarely being used these days, but although it's still being used, I think, a lot in industry, so I guess it's a good thing to be familiar with it. All right. Okay. So let's see. Here's another concentration unit you might encounter. Percent by volume. This is usually the concentration that alcohol solutions are given in. So percent alcohol, like you have a mixture of alcohol in water, it's given to you as percent by volume. It tells you how much solute you have, how many milliliters of solute you have, if you have a 100 milliliter solution. Okay, so here's an example. Let's say typical rubbing alcohol you find is going to be labeled 70% isopropyl alcohol, and this is the formula for isopropyl alcohol. The rest of that is water. Okay, in fact, technically speaking, it is the alcohol that's a solvent here, but it doesn't really matter since you have a homogeneous solution. So if 70% isopropyl alcohol, okay, and let's say the density is given to you. You can figure it, you can determine that in the lab if you wanted to. 7.786 grams per mil. Okay. So let's say you wanted 0.1 moles of isopropyl alcohol. How much of the rubbing alcohol sample would you need? Well, what's our strategy here? You have 0.1 moles. You have to change it to grams. Okay. And if you know your grams, okay, so you need, what do you need here? You need molar mass, right? If you know your grams, then you can figure out milliliters. And the way you do that is you need your density, which is given to you. If you know your milliliters, then you just figure out that that's only going to be 70% of what you would actually need. All right, so let's see. Molar mass of C3H7OH. Let's figure that one out. C3H7OH. Okay. So 3 times 12.01. Carbon is 12.01. So that gives you 36.03. And 7 you've got 8 hydrogens. Okay, 7 plus 1. So 8 times 1.008 is how much? 8.064. And oxygen, you have 1 oxygen, so 1 times 16. That's 16.00 for a total of, let me add that up, 36.03 plus 8.064 plus 16, 60.09, okay? 60.09 grams per mole. That's the molar mass of isopropyl alcohol. So what do I do now? I change my 0.1 moles to grams. Okay? So I have 0.1 moles. Okay, how many sig figs do I have there? 0.100 of your alcohol. Change that to grams. 60 point, oops, what did I just do? Times 60.09 grams per 1 mole of alcohol. Okay, so that cancels moles of alcohol. And then what do? I change my grams to mils. I need the density. What's the density of the isopropyl alcohol? It's 0.786 grams per mole if it was pure. Okay, so 0.786 grams. So 0.786 grams for 1 milliliter of your pure alcohol. Okay, this is alcohol, so alcohol cancels out. And then finally, I say that whatever this is only going to be 70% of what I need. Okay, so this is 100 mils. I'm running out of room. Let me extend this one. I don't have enough room, so let me. So I'm just going to say I'm going to need 100 mils of solution if I want 70 mils of alcohol. Okay, that's what 70% is. So what did I do here? I changed moles to grams. Okay, and then in this step, what did I do? I changed grams to milliliters of pure. Okay, and in this last step, I changed milliliters of pure to milliliters of rubbing alcohol, which is the impure mixture. All right, so if we did the calculation, you'd say it's 0.1 times 60.09 times 1 times 100 divided by 0.786 divided by 70. And that should be 10.9 milliliters of rubbing alcohol. Okay, so this gives you 10.9 milliliters of rubbing alcohol. Okay, so let's see, 0.1, oops, 0.1 times 60.09. This is 6.009 moles. Okay, so this is 6.009 grams is what you need. Sorry, 6.009 grams. And then you change your grams to mils. What do you have there? Divided by 0.786. 6.009 divided by 0.786. That gives you 7.645. 7.645 mils of pure. And then from that, you figure out that that's only 70% of 10.9, which is what you need. So the last step, you say 7.645 divided by okay, 70 times 100. That's 10.9. Okay, so that last step right there, you're changing it from the pure amount to the actual amount of the mixture that you're going to need. You would expect to use more of the mixture because the mixture is not pure. Okay, so if you had pure alcohol, you'll need 7.645 mils. Okay, you can weigh it, or you can use a graduated cylinder if you don't want to risk spilling it on an expensive balance. And then if you don't have pure alcohol, then you figure out that's a percentage of your rubbing alcohol. So that's only 70%. So the actual rubbing alcohol you'll need is 10.9 millimeters. Okay. Another concentration unit you might encounter is called percent weight by volume. Okay. For example, vinegar is, if you see a bottle of vinegar at the grocery, it will tell you it's 5% acidity. And that simply means that it has 5 grams of your solute, which in this case is acetic acid, CH3COOH. Okay, so vinegar is typically like 5% acidity. It's 5 grams of acetic acid in 100 mils of the mixture. Okay. Commercially available solutions of glucose that's typically used in hospitals, okay, is 5% weight by volume. So if you need 0.01 moles of glucose in an experiment, how much of that glucose solution would you need? Then again, you say, okay, I know moles. I can change my moles to grams. Okay. If I know how many grams I need, then I can just say 100 mil is going to give me 5 grams. So I'm just going to multiply that by 100 mils over 5 grams because my percentage by weight is 5 grams, and this is going to be the volume of solution you're going to need. Okay, so let's do that. What's the molar mass of glucose? C6H12O6, and that should give you 180.1 grams per mole if you did that. So change grams to moles. Moles to grams, 0.100 moles times 180.1 grams per mole. That gives us 18.01 grams, 3 sig figs, okay? So first step, convert moles to grams. You figure out you're going to need 18.01 grams. Second step, you can say that that's 5% of what you need, okay? So you're just going to say then that 18.01 gram that you need, okay, you can take that out of your solution. So that's, you can just continue on here. You can say 100 mils of solution is going to give me 5 grams. So you can use that as a conversion factor. So you can you can cancel grams right here. So here I figure out I need 18.01 grams of the pure stuff, but since it's not pure, I have to get it from a solution that has 5 grams in 100 mils. this second step right here tells you how much you actually need. So 18 points. Okay, so you have 18.01 divide times 100 divided by 5. That means I'm going to need 360 milliliters of solution. 360.2. Okay, so 3 sig figs. So I'm going to need 360 mils of that solution if I want to get 0.2 moles out of that solution. So final question, what is the molarity of this particular solution? Well, how many moles do you have? If you have 5 grams in 100 mils, 5 grams, change that to moles, and 100 mils of solution, change that to liters. Okay, so you can say 5 grams of glucose times 1 mole over 180 grams, 80.1 grams, equals, so 5 divided by 180.1 is 0.02776 moles. Okay, 0.02776 moles, and my volume is 100 mils, so 100 mils is 100 times 10 to the negative 3 liters, okay, or that's 0.1 liter. So I have 0.02776 over 0.1 liter. I'm just treating everything as exact. So that gives me 0.2776 moles per liter. Okay. I'm just rounding it up to 4 sig figs. So if it was like 5.00% by volume, weight by volume, W/V, then that means I'm going to have, that's the molarity is 0.278 moles per liter. These numbers are just exact. I just rounded up to 4 sig figs. Okay. So that would be your molarity for your glucose solution. All right. Or you could have done that by simply dividing the 0.1 moles by 0.36 milliliters, and you should get the same answer. Because any amount of solution that you have, if you take the moles to the volume, the ratio of the moles to the volume of the solution, you'll always get the same answer, same molarity. Okay, so that's molarity. Okay, hold on. Let me just stop the